All right, good afternoon. Thank you all for coming. So it's truly a pleasure for me to share what I learned about FLUORO-SORB products in the past 8 months. Actually, I was a grad student in Purdue University, years ago, in Indiana. So Chicago was the #1 city for me for a long weekend getaway. So it's very nice to be back. Before I start, I'd like to acknowledge my students, so Dr. Bei Yan, Chen Yang, and Gabriel Munoz, who did all the work. All right, so I'm not going to go into the nomenclature much, and I know it's a crash course for a lot of you to capture the chemistry, but I want to just take the mystery out of the name, So there's two parts, per and poly. Per is very small in terms of number of species. So you're talking about pers right here. PFAS and PFOA, and their structure analogs. Everything else are poly. Okay, everything else here show poly. So AFFF that contain an incredible variety of PFAS species. So these ones on the left are the common targets, and that's where the most focus is. But since I'm a university professor, I want to do a little bit more. So since I have the capability, I want to push a little bit more because I think in the future, we might actually likely expand to more PFAS. So I want to be a little bit ahead. Another thing I want you to look at it is, despite all these complicated structures, they are all surfactants. Cationic one, anionic one, or sweet ionic ones. Or they have a lot of nitrogen or sulfur-containing functional group. For you, you don't have to know everything. Just, our major focus are going to be on these ones. Just going to skip here. So in terms of knowledge gap, you all probably know that remediation PFAS right now mostly focus on the water and focus on called anionic ones, like PFAS and PFOA. But my research data and also some of the others have shown that there's other things that's important. For instance, here, 4 soils we're going to discuss today. And the blue ones are the anionic ones. That's most people focus on. But for some soils, the cationic one or sweet ionic one make up pretty large fraction, like 20 to 40%. And also for water treatment part, right now there's very limited options, especially when you want to apply in large scale. So I want to cover a little bit soil treatment, where I think is going to be the future direction, but I want to expand to other PFAS as well. So I'm mainly looking at 2 products, 100, that's for soil treatment, and we are looking at especially for reducing PFAS leaching from soils. 200 is for groundwater treatment, and I'm going to make a competitive assessment with GAC, ion exchange resin, and also a commercial biochar product. So in this particular work, we measured total of 49 PFAS for which we have authentic standards. So no matter which list you're looking at, if it's US EPA 24 and there's ASTM method for soil 32 or 29, this list is broader, so it covers all those analytes. But also, so the ones in these red boxes are the ones, okay, I think laser pointer is not working. But the ones in the red boxes are most likely you're going to see in the regular US EPA or ASTM methods. But the ones on the right bottom corner are a few new ones that we actually have authentic standard synthesized. That's where I want to have a little bit more focus. So all the analytical methods we use have been published. I'm not going to go into the details. Just a note that these are not the standard methods, but I believe they are better. Okay, so that's the reason I recently got funding from startup, and we're going to actually try to develop our analytical methods into some kind of draft US EPA method. So that's work ongoing. I think in the horizon of 2 to 3 years, I hope to be able to kind of share my methods with the larger community. So I'm going to talk about soil leachate treatment or soil treatment, about groundwater treatment, but they are kind of related. But for soil leachate treatment, you can think of it as a 2-step process because PFAS kind of actually sorbed in soil. First step, PFAS have to desorb, okay, in the aqueous solution. So there has to be water there. And then dissolved PFAS is going to be taken up by adsorbents. So two-step process. For groundwater treatment, it's pretty simple. Usually you can visualize or simplify as a one-step process because PFAS already dissolved in the solution. So FLUORO-SORB 100 was tested along with carbon F400 and a commercial hardwood biochar. Biochar because it's low cost, and this is a biochar we tested in the lab. Actually, we're able to taking out PFAS, but we only tested with lab prepared deionized water solution. We have never challenged it with real world water or soil. And for soils, so 2 soils from Canada was gifted to my lab by Environment Canada, and 2 US soils are from US Air Force Base. So the soil collection kind of was supposed to be random, but somehow they turned out to all be sandy soils. And I think for a lot of firefighting sites, or the sites that you guys are probably going to look at in the future, a lot of them kind of just bare, there's not much vegetation. So I don't think it's surprising that they tend to be sandy. The organic matter is low. Cation exchange capacity range from low to high, and the pH covers a nice range from 6 to 8. Let's look at total PFAS concentration. So nanogram per gram. So because we were looking at 49, so the number tend to be higher because we're looking at more compounds. The lowest one is about 1.8 ppm, if I convert to ppm, and the first one from Canada was highly contaminated, about 60 ppm. So, soil can retain so much of PFAS, and in the source zone, they could very likely be long-term source of PFAS in the aqueous solution. So that's why, it's very important to look at the source, look at the soil.
What's the size of all 3 products? Like, what kind of mash or the micron size?
So FLUORO-SORB 100 we used it is. And F400 and the biochar, I think we sieved it down to get rid of the large grains, I think about less than 2 millimeters. We basically did very little modifications, and I'm basically just going to make the size range relatively uniform. And I don't really think the particle size for these products really had much impact. It's just for us to get a little bit easier to handle in the lab.
And you measure CEC. I see the soil quite different. The one has the highest concentration, has a higher CEC. So that's results, or that's the cause of the higher PFAS or in that soil?
I don't think so. Especially if you look at the first 2 soils, they have very similar clay contents, and their sand contents are similar. So I can't tell for sure. It might be just one soil from a very kind of heavily contaminated place, and the other is less. We don't know the history of any of the soils, so all come from more or less kind of Department of Defense or kind of Air Force bases. Okay, so when we started, the first challenge we faced was, we're doing soil leaching. There was no standard or widely acceptable like a leachability test. So we had to start from somewhere. We just used USEP method 1311, also known as TCLP test. We did in-house modification because that method was not really developed for PFAS. So we got rid of all the glass containers. We shrink down the size. We also remove all the filtration steps where that artifacts could happen because filters tend to absorb PFAS. We got rid of all those steps. So that the first step would have to generate PFAS leaching profile as a kind of control starting point. And then we have to decide, we were doing lab tests, how we can able to simulate the natural condition, but we'll be able to do it in a way in a short period of time in the lab. So we have to decide, how long you have to shake it, kinetics, also sorbent dosage, also the solution pH. And then after we kind of narrow down the set of condition, and then we're going to use it for competitive assessment. So just a simple procedure, 5-gram soil, certain amount of sorbent, or when you just want to look at leaching profile, no sorbent added, and 50 ml of deionized water. And then we shake it on a large shaker for up to 8 days. And the sample preparation was very actually straightforward because there's really very high concentration PFAS. There's really not a lot of preparation need to do, which is do high-speed centrifugation, get rid of solid, and stabilize the PFAS in organic solvent, and then use LC-MS for analysis. So we have two systems. One is hydrolucent, the other is just regular triple quadruple for quantitation. First, I want you to look at the PFAS on soil. So on the left. On the right is PFAS that can leach out from the soil. So same color scheme, blue one represent anionic one PFAS are the ones that most regulation target. And orange is the threonic ones, and gray are cationic ones. So our study have shown actually all the PFAS are leachable. But the percentage of leachable for each PFAS really varies with soil type or PFAS type or maybe solution chemistry. This is where we're just starting to scratch the surface because cationic PFAS, right? You probably haven't heard about it, right? You're just scratching the surface. So there's a lot of we are going to look at it. But if you look at the leachate, if you look at the blue bar, it's getting smaller. So anionic PFAS for U.S. soil too in the leachate, it's actually less than 40%, and there's a lot of other things in there. Okay, so a little bit more detail on the PFAS distribution so out of 49 PFAS we analyzed for each soil we can detect about between 21 to 32 different PFASs. And somehow, I'm just listing the top dominant 6 ones. If you look at all of them, PFAS was always the number one. So targeting PFAS, there's nothing wrong about it. But if you're looking at the color scheme, the blue ones, anionic one, that's where people mostly been focusing on. But we have orange one, we have the gray one. So those, we see them on the instrument. I know there's no regulation, but when I see them for a researcher, I can't hide it. I just want you guys to know there's a lot of PFAS out there. And the concentration that can leach out between 168 to close to 4,000 ppb when we did the initial test. Just a second. So the question is, what instrument did we use for analysis? For this data, we use high-resolution mass spectrometry called a Q-exactive Orbitrap. So there's a few other brands that they're just as good. Now let's look at the kind of kinetic. Right now we're still trying to figure out, what would be best condition to test these materials. So the top 2 lines on the top are just the control. That's where there was no sorbent. Soil plus water, you shake, see how much PFAS can come off soil. And it takes about 1 to 4 days for them to reach equilibrium. And the other lines on the bottom are the one in the presence of the FLUORO-SORB 100. So the dosage we use is between 0.1% to 5%. So this is relative to the mass of soil. For 0.5%, that means for every 5 gram soil, you need to add 25 milligram of FLUORO-SORB 100. So it's a pretty low dosage. But very clearly, just when we start to increase the amount of sorbent, you can see the lines getting lower and lower. And for 0.5% a low dosage, the total PFAS reduction was more than 87%. A little bit more, let's look at individual ones. So on the left, the table there was no sorbent. That's just a leaching profile, so I give you a background where we are starting from. And then on the right, we are looking at the 6 dominant PFAS. So 3 blue ones, anionic ones, the one everybody targets. They actually were kind of quickly removed. The y-axis is removal efficiency. You want to get to as close to 100% as possible. So more or less, they can get more than 90% or more. For the orange ones, the new PFAS, they're called the sweet ionic one, neutral ones. It really vary from compound to compound, somewhere between 50% to 90%. At this particular low dosage, and then one of the cationic PFAS, there was almost no removal for that low dosage. Now let's look at a wider range of dosage. Still on the left, that's the control. very consistent with previous slide. If you look at the blue one, anionic ones, PFAS, those are dominant ones, really come to like a 0.5% or 1%. In terms of removal efficiency, at least the data didn't show you much difference. But when you look at actual PFAS concentration, like gone down to really, really low, they did make a difference. But if you look at the number here, it doesn't really can't tell the difference. But difference start to show when you're talking about the new PFAS, serial ionic ones or cationic ones. You can clearly see a dose response. The higher, the more more adsorbent there, the more removal that would happen. For cationic ones, remember earlier, 0.5% no removal, but when you increase it to 5% of FLUORO-SORB 100, it was close to 80% removal. So I haven't seen literature a lot about other sorbents in terms of performance towards this kind of a new PFAS. Let's look at entire profile for this particular soil. For on the left, no sorbent, that's a leaching profile, and PFAS was the dominant one. After adding 0.5% FLUORO-SORB 100, and PFAS kind of go from 3,000 parts per billion down to about 10 parts per billion. So kind of fall behind the other PFAS. If we increase further, 5%, and PFAS was reduced to less than 1 parts per billion, so 99% nice sort of removal. And you look at across the board, and you see the bars getting bigger on the right because there's a lot of PFAS that were totally removed, and we couldn't even detect them. And if you look at y-axis, 3,000 versus 50, you see across the board, all the PFAS were reduced. So up to this point, what I want to actually show, this is still the stage where you're trying to figure out the best condition to use. So we decided, okay, we have to shake it for at least 4 days to get to equilibrium. And we decided to kind of, from this point on, to look at a low dosage rather than a high dosage. The reason, because when you use high, everything's removed. It's really hard to tell the subtle differences between different soil or different materials. So we decided to use not really a very low dosage, 0.5%. But one thing we didn't answer was a question regarding the solution pH. So if you are familiar with the EPA methods, 1311 was only for acidic condition around pH 5 or sometimes even lower. But some literature actually shown that for PFAS, absorption to soil or sediments, actually at higher pH, there's more PFAS tend to be leaching out. So we were a little concerned that maybe we weren't testing the worst case scenario because we were using the low pH condition. We should have tested high pH. So we did another test to look at impact of pH, go from 4 to 8. And our data didn't show any impact of pH. So at this point, I feel very comfortable to kind of move forward. But also, in terms of the leachability test, really, it's studied by itself, and it's really up to US EPA or other regular agency to come up with a method that people can use. We also found ionic strengths, for this narrow range, also did not have any impact. All right, so now these are the key data. So comparative assessments, I'm just going to list a few compounds here. And so I want to see, so on the bottom table is where we start. So PFAS profile concentration in the leachate, okay, before you add any sorbents. And so the number between 62 to 3,000 parts per billion. On the top table and the right figure, they have the exact same information. Just look at the blue bar. So that's the FLUORO-SORB 100 in terms of removal of PFAS from the leachate. And across the board, 99% 9 or 90.3 removal across all the different soils. For GAC, that Calgon F400 carbon, for the 3 soil on the right, relatively low concentration to start with, but still very high. If you detect 100 ppb in the field, you're going to freak out, and this is something definitely have to treat. But in this case, we consider them relatively low, and you can see removal between GAC and FLUORO-SORB 100 was no difference. But difference start to show up when you're talking about a highly contaminated soil. The very first one, Canadian one, and GAC reached to 74% removal, but FLUORO-SORB is 99% non-removal. For biochar, I'm not going to mention too much about it. Really, we thought it was a good product. It really didn't work when you come to the real world situation. And you may see the negative numbers. Have you seen negative numbers in your studies? I don't know if you guys look at report. So negative number is not uncommon. So analytical variance for this kind of analysis can be plus minus 20%, even 30%. So sometimes when things don't change, you can still see minus 30 number. But in this case, it's a little bit something else was going on, so we don't know yet. So this is only PFAS with addition 5% FLUORO-SORB 100. Let's look at another compound. So this is the one that's, this is actually sulfonamide. If you look at the structure, if you remove the nitrogen or oxide nitrogen, you're going to become a 6-carbon analog of PFAS. So this compound we detect a lot, so we couldn't ignore it. But in terms of its performance, it was very similar to PFAS. Except for this compound, if you look at concentration in the leachate between 9.9 to 86 parts per billion, not really high, but if the regulator is going to set something like parts per trillion level, this is all compound to have to watch for. I'm not going to go through all 32 of them, so I'm just going to give you a couple examples. Let's look at the total. So for this particular one, let's total remove looking at the 3 soils on the right, relatively low concentration. So GAC performed slightly better than FLUORO-SORB 100. Well, we didn't put an error bar. We should have put an error bar there. But when you come to the most polluted soil, you clearly see the difference. One is 90%, the other is 75%. Biochar, just another message, don't use biochar. Again, we wasted 2-3 years time testing and don't use it. Okay, just a quick summary before I move on to the groundwater treatment. So just non-ionic PFAS can be important components, and you may also heard the word about precursors. The precursors, at the same time as the polyfluorinated, or mostly non-ionic ones. So this could be important in the future. I'm talking about maybe next 5, 10 years, or 20 years of horizon. And so FLUORO-SORB 100 performed really well for anionic PFAS. That's most where the regular targets are. And also, even for the newer ones, FLUORO-SORB 100 worked pretty well. Overall, performed better than GAC. And also for PFAS heavily contaminated soils. If you don't really reach to the drinking water level, even for soil leachate, you can really just look at the dosage. The more you add, the more you can remove it. Any question before I move on to the second part?
The dosage of the GAC, was that the same dosage as the FLUORO-SORB?
Exactly the same. Exactly the same. All right, let's look at groundwater treatment. So FLUORO-SORB 200, similar to 100, and GAC carbon 400, biochar. We were doing the work at the same time, so if I knew ahead of time, I wouldn't have been spending time on biochar. And then we also tested the ion exchange resin. So there was this particular resin was a component of Rhine-Bine products from Australia. And let's look at the PFAS profile of the groundwater. So the groundwater also from US Air Force Base. Total concentration 65 microgram per liter, parts per billion. So even though we tried to detect 49, but actually this groundwater, mostly you're seeing are anionic PFAS. So those ones on the target. So these are the ones in the blue box are more, a little bit higher concentration. So will be kind of arbitrary, which one is higher will be arbitrary. But these ones tend to be one appear almost in every groundwater sample you're going to look at it. And the exception is this particular one. And we actually just saw this compound. It just appeared quite high, so I have to include in there. So in total, I think it's 16 PFAS. So groundwater, I think overall tend to be more of the anionic one, typical ones that you see, not so much of the new PFAS. We also look at water chemistry. So it turned out this water was very clean. low TOC, low COD, low BOD, and we actually have it analyzed for more than 100 different type of organics. Only 2 species that kind of show up above the detection limit, acetone and diesel. So very clean groundwater, but not for PFAS, right? And in terms of experimental procedure, so for every 500 milligram of groundwater, we added in between 5 to 40 milligram FLUORO-SORB 200. So this is where we were trying to develop the kinetics and the isotherm, typical testing we do for sorption type of experiment. And we were limited by how much sorbent we can add, and because we can't vary the concentration of groundwater, only thing we could do was just vary the amount of sorbent you add. So 5 milligram was lower, because below that we could hardly measure them out accurately. 40 is the upper limit, is because the more we add, there's no PFAS left, and we couldn't analyze for them. So these are range we work on, slightly narrow. The rest of the procedures are similar, similar to the soil leachate treatment. So out of 16 we detected, I'm just showing data for 12 of them. So these are the kinetics. How long does it take for them to kind of remove from the solution? Over time, you're supposed to see them reducing in concentration in the solution. So higher sorbent mass, faster they kind of go down, and they also go down further. And overall, it took at least 5 days for them to reach equilibrium. Only one, the very last one, takes a little bit longer. So overall, we did 7 days for the test, for isotherm test. And so here's absorption isotherms. Are you familiar with absorption isotherms? More or less? Okay. So if you're familiar with isotherms, and you can look at the data, you're going to say first thing, they don't look like good isotherms. The first one, a few dots here, and some kind of a linear. If you look at C, that seems linear, but a lot you see this kind of S-shaped isotherm. So this is pretty unusual to see this kind of S-shaped isotherms. And we're still trying to figure out why. So we give a name is when you combine different isotherms, you want to do mathematical fitting so that you can predict. We actually use a combination of linear and Langmuir type, so we call piecewise isotherm in order to predict. If you look at the fonts are a bit too small. If you look at the range and axis, they are pretty narrow range. That's because limited by the amount of PFAS in the groundwater, so we don't have a large room to play with. So we want to still, because the groundwater was so diluted, we really couldn't actually test out the full capacity of the material, but someone else is going to talk about later today. But we still want to kind of see if we can expand a little further. So the white region are the one from the Air Force groundwater. The blue region is where we prepare water in the lab, so we are able to add a lot of different compounds and to challenge it for higher concentration. So I'm only showing the data for the top 4 most important anionic PFAS that occur in groundwater, especially in AFFF-impacted sites. I call it region 4 because it's just kind of continuation from the previous slide. And so absorption capacity, if you look at the number, milligram per gram. So PFAS was able to reach 31 milligram per gram. And the second one in the middle is PFHXS. It's 6-carbon sulfonates, very similar to PFAS, 14. For PFOE, 20 milligram per gram. And for 6,2-fluorotalumar sulfonate. For those who are not familiar with this one from like DuPont products or fluorotalumar type of chemistry, is also appear in very high concentration. So this compound capacity was about 25 milligram per gram. So still, the isotherm kind of unusual. We have to use another combination for Langmuir from each isotherm in order to kind of describe the shape mathematically. And let's look at comparative assessment. Let's look at this one. So this is 40 milligram sorbent for every sorbent material, 500 milligram groundwater after 7 days of shaking. And let's look at the total. So a lot of information. Let's look at total, and ion exchange resin performed the best. Got to removal efficiency 94%, followed by FLUORO-SORB 200, and followed by GAC and biochar. And for GAC, somehow, if you look at the gray line in the middle, if you look at the gray bars, somehow this GAC performed very similarly for each PFAS, more or less 50, 60%. I don't know why it was like that. So we want to look at the bars above the gray line. Long-chain PFAS. You always heard about long-chain versus short-chain ones. So PFAS are considered long-chain ones. So if you look at PFAS, FLUORO-SORB performed a little bit better. If you look at PFOA, ion exchange resin performed a little better. But I think in the long-chain PFAS range, we believe ion exchange resin and FLUORO-SORB 200 perform very similarly, overall better than GAC, than biochar. And look at the short-chain ones. A short-chain one, right in the blue one, that's a 5 carbon, and that's a 4 carbon one, the two ones. And you see ion exchange resin remain perform pretty well, followed by GAC and followed by FLUORO-SORB 200. And then biochar. But I think there's some later data show that from different tests that FLUORO-SORB also performed pretty decently for a short-chain PFAS. All right, so one thing we did is after we did the sorption test, remove PFAS from the water, we also want to see if the sorption was reversible. So after the test, we remove all the groundwater. We add in equal volume of deionized water to see if anything would leach back. And so this data is a little bit kind of scattering, but the one way I would look at it when you deal with PFAS work is for consistency. All right, you're going to see random data points here, there. But consistency is the most important one here is where when I change different sorbent mass, do I see a consistent response? So these ones, we actually saw some desorption. I will now say efficiency or percentage between 1 to 7%. Remember, previous slide, we removed more than 90%, and some of them, at least for these two compounds, some seem to leach out a little bit. But everything else, you see some large data points. Sometimes maybe just one data point is really high, kind of, give you a really large bar, but there was no consistency. So I would more focus on the one with the consistency. But overall, there was very, very little kind of leaching of the PFAS that was taken up by FLUORO-SORB 200. So we concluded at that time, I think the sorption was almost non-reversible. Why was such a strong interactions? We just look at the mechanism a little bit. So we ran FTIR analysis, and we saw, okay, so top one, blue one is PFOA only. In the middle is PFOA taken up by FLUORO-SORB 200. Bottom is FLUORO-SORB 200 only. So we see a little shift in the carboxyl group, and that means phase transition, and that means there's a kind of very strong electrostatic attraction. So that might be one of the mechanisms that kind of holds PFAS tightly within FLUORO-SORB 200. There's going to be filter work done to understand why the material performed very well. In the end, so I'm almost to the end. In the end, we also want to challenge this material with real water. So real groundwater, you're going to see co-contaminants. So we selected some co-contaminants like diesels, BTEX that you would commonly see in groundwater. So we started with diesel, and the concentration we selected was based on a recommendation from a consulting firm, is the range they often see in the real groundwater. So we found that at high concentration, up to 100 milligram per liter of diesel, not only the performance was not impacted, there was actually enhancement of the removal. So we don't know exactly why yet. And also we challenged with another co-contaminant is natural organic matter. So we bought a standard natural organic matter from International Humic Acid Society, because everybody buying same source so that you compare them. And we really add a lot of natural organic matter. You're not usually not going to see 100 milligram per liter of natural organic matter, but we just want to challenge it. So you do see that after you adding a lot of natural organic matter, the reduction was about 30% for most of the PFAS. But if you are familiar with the treatments using GAC or active carbon, and the 100 milligram per liter basically gonna kill the carbon. It's gonna block the pores for GAC, and you're gonna lose maybe, there's efficiency gonna be reduced by 10 times or more. So in the future, we're gonna try to do a comparative assessment under the same conditions to see, how much GAC would lose the capacity relative to FLUORO-SORB 200. And in the end, we look at BTAX, TCE 1,4-dioxane, between 0.01 to 1 milligram per liter. And if you look at the bars, they're all very even. There was no impact at all. And this tells me that these materials are pretty robust and they're pretty resistant to fouling by other kind of co-contaminants. In the end, we also try to look at a little bit water chemistry, but this is just starting. So we look at adding a little more calcium or adding a little more sodium to see if there was any impact, because we were using the groundwater, so itself has a lot of calcium to start with, so we have to raise a little bit more to 100 to 150, and sodium up to 150 milligram per liter. You're gonna see the bars all even, so it's just no impact at all. So, so the water hardness or ionic strength seem to have a little impact on the removal by FLUORO-SORB 200. So pretty robust material. Okay, just a quick summary of the groundwater treatment. And so material was superior to GAC 400 and biochar and comparable to ion exchange resin for most of the PFAS. And then the material appeared quite robust and should be able to function in various kind of type of groundwater. In the end, since I'm an engineering professor, but it doesn't mean I'm more qualified, but I'm probably the least qualified one to make engineering recommendation because I never practiced. But anyway, I just want to kind of throw in a few messages I want to share. It's really up to you, to take it or not. Just my personal opinion, not of any of the SECOs. Okay, so if you are the ones that want to follow kind of all the guidelines, regulatory targets, care about only removal PFAS, PFOA, or some of the other anionic PFAS, FLUORO-SORB 100, 200 seem to be very efficient and cost-effective, I assume. If you're the ones trying to kind of cover everything, I just absolutely want to remove everything. And pre-treatment, or most of the treatment using FLUORO-SORB would work. In the end, you want to maybe add a little bit polishing step using GAC or ion exchange resin. That, I think for a lot of people, they feel more comfortable to especially for drinking water, to have GAC or ion exchange resin in the end, right? You like that polishing step. If you decide to use it, you want to actually test it in the lab prior to apply to the field. One thing to remember is you have to test it for sufficient long enough equilibration time. It's not only for FLUORO-SORB 100, 200. For GAC, exchange resin, the same thing. You have to give a long enough time to really understand its capacity. As far as the dosage, it's really hard for me to tell. It's really soil dependent, groundwater chemistry dependent, or type of PFAS you have in there. In terms of isotherm, this is where things get a little bit complicated because we see the funny S-shaped isotherms. So we couldn't come up with just a single value that people want to use, like called adsorbent coefficients. You want to get that 1 log KD value, right? It's very hard to do that because you have that range. But I think for this particular groundwater, we did compare, and that log KD value was somewhere between 4 and 5 for different PFAS. So that's usually, extrinsic resin or GAC. Some of the GAC may be able to get that level. The last thing I want to talk about is you see negative numbers, or you see things magically appearing in, in soil, in groundwater. It happens all the time just because there's a lot of PFAS out there. There's transformation process going on. All the poly ones eventually give long enough time would become per, okay? So, when you test it, see negative numbers, I see that very often in publication, in reports, it's common, okay, because there are other PFAS out there. You have to think about it. That's it. I thought I have an acknowledgement slide. Okay. Well, I want to just mention that in the end, so this is actually the work was a collaborative work between SACO and also actually part of work also funded by actually NSERC, Canadian Funding Agency, equivalent NSF. So because we are looking at not only the performance in the future, we also want to understand why this material performs that well. With that, thank you for your attention.
Hello, I have a question on the isotherms, particularly the groundwater.
Yes.
You're using 5, 20, and 40 milligrams of various adsorbents.
Yes.
What was the size? Do you do any size reduction on the carbon or the resin?
No, I don't think so. We did rough sieving because they do have very large particles. Mm-hmm. But other than that, we didn't do anything.
Okay. Thank you.
No problem. No questions? Think I'm good? All right. Okay, thank you.
Thank you, Jen.